and started all the calculations. So we did the shear and moment diagram, established where the maximum shear and moment values were, figured out the cross-section properties, the geometric properties, and then calculated the stresses at each point that would be necessary for accurately drawing the stress distribution along the cross-section, right? So the next step then would be to draw those stresses on a sketch representing the cross-section. So if we draw the shear stresses first here, I'll just start with a vertical line. I'm going to use a different color. All right, so we had for shear stress, we had 0 at the free edges, and then at this location, I'm just going to draw a horizontal line to help me out there, we calculated a value of 0.44. And then that represents, right, the outer edge or the bottom edge of the flange. And then once we get to the inside corner and we have less thickness, that shear stress jumps to 1.32. And then the maximum value at the neutral axis we found to be 1.44. And then back to 0 at D. So the parabolic distribution between points would give us a profile that looked something like this. To represent the magnitude. And then for direction, how do we know what direction that shear is going? Let's go back to the first page of the problem. Think about the loading, shear diagram. What can we tell from that?
Positive shear.
We have positive shear, exactly, so that's the right start. And what does the positive shear tell us about direction? If we look at the sign convention for positive shear, and we consider the right side of a segment, it's going to be downward, right? So that's how we would interpret it in our stress sketch, right? Shear flowing downward. So is that positive or negative shear stress in physical space?
Physical space.
Think about Moore's circle and our definition of shear stress sign convention. Negative, right? Yeah. It's a little bit exasperating because we go from positive shear to negative shear stress in the same interpretation. And it gets even better because I am going to, when we get to that Moore's circle part of the problem shortly, I'm going to add a clarification regarding the sign convention of shear stress on Moore's circle. So shear stress sign convention is just a world of fun. But anyway, the most important thing is getting the actual direction correct, right? And then the sign it can trip you up in Moore's circle, but it's not the end of the world if you get the actual sign wrong, as long as you can understand what direction it's flowing. That's the most important thing. All right, so then for the bending stress, we have the line representing the right face of our section, and then we had tension in the top with a maximum value of 17.75. We know it's going to be 0 at the neutral axis, and it will vary linearly between those points. And then compression maximum value calculated as 28.25. So you can either continue that line straight through the cross-section like that, or you can draw it on the right side with arrows pointing towards the cross-section. Either way is acceptable, as long as the arrows are pointing in the right direction. All right, so we'll label that as our sigma, and all values are KSI. So want some note of units on your diagrams. All right, questions? Okay. All right, so then part B of this problem was asking for the principal stresses at the location we marked B minus, so the top of the web. And so we want to identify the stresses that are acting at that location on a stress element. So at B minus, we found our shear stress, well, I'll just say what we're doing, right? Principal stresses. I think we were also asked to find the maximum shear stress at B minus. So our stress state that we have is tau xy being 1.32. Sigma x is 17.1. Nope, sorry. I read the wrong line there. Normal stress was 8.55 at that location. And sigma y is 0. Because the only relevant stress we have is normal stress, or the only relevant normal stress we have is in the x direction. So our reference point on Moore's circle will be 8.55 and negative 1.32. All right, since we have negative shear stress. Or wait, no, what did we say? We said, yeah, that's negative shear stress. That's right. All right, because we had shear in that direction, shear stress in that direction, so that's negative in the physical space. For shear stress. All right, so the center of the circle then is going to be the average of the two normal stresses, so 8.55 plus 0 over 2, 4.3, rounding a bit. Radius calc will be square root of 4.3 squared plus 1.32 squared, which gives us 4.47. So if we plot our circle, I'm going to draw a circle, horizontal axis. All right, there's our center. Here's the principal stresses that we're after. our reference point would be somewhere here, right? 8.55, negative 1.32. And so our first principal stress is just C plus R, or 8.75. And second is C minus R, or negative 0.2. And of course, the maximum shear stress is the radius, 4.47. So now we can draw in the vertical axis representing the shear stress. And this is where I would like to add a comment related to the sign convention in Morse circle on shear stress. So when I presented it to you in class, I said, we'll just plot positive shear stress values on the lower half of Morse circle, right? And that is great, that's perfect if you're using the right face of the stress element as your reference point, right? Which is how these notes were developed, and even the example in that lecture refers to that. So the caveat that I forgot to mention is that the real definition of sign convention on Morse circle, that the one that we're adopting in this class, is that it is, all right, so as a refresher, well, we'll use this example as a demonstration. So we had this stress state, all right, something like this, nothing on Y. So using the right face, we have negative shear stress, which plots above Morse circle. The negative shear stress on the right face tends to cause a clockwise moment about the center of that. So the positive Morse circle shear stress being plotted below the axis is the value that would cause, or the direction I should say, that would cause a counterclockwise rotation about the stress element. That means, if we go back to the Morse circle lecture, all right, so this is one of the examples that was in the handout from that lecture where kind of everything is just laid out. Here's the positive stress definition in the context of physical space, all right, and then procedure summarizes, all right, use the stresses on the face perpendicular to the x-axis, that's the right face, plot your points, all right, and then vertical axis shear stresses are positive downward. So again, this is consistent with this. If you were to use this face as your reference point, it would change the sign of the shear stress on Morse circle, right? So we can see that when we go to Morse circle, for example, remember Morse circle is twice the rotation of what you would have in the physical. So directly opposite our reference point should land us at sigma y equals 0, right? So that's what this point opposite our reference point represents. It's the 90-degree difference in the physical, 180-degree difference on Morse circle. So notice that it has to be the opposite sign of shear on Morse circle in order for that to work out, right? So what this means is basically if you use the right face consistently, things simplify. You don't have to do that extra thought process. If you use the top face, for example, you just have to think about that shear stress sign convention a little bit more. So if you already did your homework 3 and you decided to use the top face instead of the right face and you missed that point, and you got the sign convention wrong on Morse circle, that's okay, you won't lose points for that. I'm guessing everybody probably just used the right face though. But it was worth clarifying that in this lecture, right? Any questions? Yeah?
Are you just saying if we use the top face that our reference point would be at the 0 with some sort of shear, and then as far as rotating?
Yeah, so exactly, yeah. So in this example, if you were to use the top face or the bottom face, right, because whatever, you'd have that, right? So if you were to use the top or bottom face, either of those would cause a counterclockwise rotation about the center, right? So that would plot your shear stress below the x-axis, or below the horizontal axis. And so then your point would be sigma y, and then the positive tau, which would be right here. And it would be opposite that one. So you would use that as your reference point, and from there you could calculate, whatever, yeah. So yeah, either of those approaches are fine. You just have to make sure you're keeping track of the shear stress sign convention. So, fun stuff. All right, so moving on. Now we got the beam deflection. This won't take too long to go through, and then we'll get into the fun topic of beams on elastic foundation. So for beam deflection, all right, we've got just one span to consider, right? The loading is a constant uniform load over the entire span. So we only need to make one section cut and obtain one moment equation. So if we make a cut through our beam and always measure x starting at 0 at the left end and increasing to the right. And we draw a free body diagram of the right side of that cut. All right, we've got the load of 2 kips per feet acting over a distance of, the total beam length was given originally as 10 feet. So this distance would be 10 minus x. And that cut exposes internal shear and moment. We're only concerned with the moment for this evaluation. So I'm going to note that as m of x. So then from equilibrium, of that right side of the cut, we can find an expression for m of x, which is going to be -2 kips per foot times the distance over which it acts to get the resultant force, and then multiply that resultant force by the moment arm to the cut, which is going to be 10 minus x over 2. So this simplifies to negative quantity 10 minus x squared. And since moment is equal to EI times the second derivative of deflection with respect to x, we set that equal to negative quantity 10 minus x squared and integrate that expression twice to get our deflection. So we get EI times lowercase v of x is equal to negative quantity 10 minus x, and that whole quantity to the 4th over 12 plus c1x plus c2. So now we need to apply our boundary conditions. which I'll probably just abbreviate from now on in this class as BC. So in this case, we have our boundary conditions both come from the fixed support. So at x equals 0, we know deflection is going to be equal to 0. So that will tell us that C2 is equal to 10 to the 4th over 12. And then our other boundary condition, at x equals 0, we know slope is going to be equal to 0. So then if we get our equation for slope, which would be the first integration of the moment equation, we have C1 equal to negative 10 cubed over 3. So our result would be one over 12 EI, so we don't want to forget about the EI term in the final equation, times in brackets 10 minus x quantity to the 4th plus 4,000x minus 10,000. Or you could simplify it differently, and maybe it looks something like 1 over 12 times x squared over EI, and then after factoring that out, you'd be left with 600 minus 400x plus x squared. All right, so everybody's brain works differently. Everybody simplifies things differently. As long as you make some kind of effort in problems like this towards collecting like terms and providing an answer that is reasonably simplified, that is good enough for me. Questions? Okay. All right. Yeah, so before I forget then, since we talked last week about those beam tables, remember when we were looking at superposition and there are all those hard to read beam configurations with slope and deflection equations, right? I did find in the FE handbook, for those of you who haven't taken the FE exam yet, just might just be nice to see. This is what is provided, at least based on the latest version that I was able to access. So there's 3 pages of these tables. Again, not as comprehensive as the ones that you have in the notes for this class, but sufficient enough to get you through that exam. And I think the example that we looked at, I remember I said, I don't know if the FE tables would be something that you could use to solve it, but looking through it, it should be, because I think the one in question was the distributed load over half the span, and they do have that one in here. So, so it's a pretty good representation of the different scenarios that you have. So one page is just simply supported beams, one page is just cantilever beams, and then the third page just has the one entry with for piping segment. Okay. Oh, that's even from a different textbook. All right, so the first 2 pages are taken from a Mechanics of Materials textbook, and then this one's taken from a Mechanics of Solids textbook. So, but there you go. All right, so now we're going to shift gears, think about beams on elastic foundations. It's a pretty cool topic. We're going to spend a couple lectures focusing on the analytical solution of this particular problem. And then later, when we get into finite element analysis, I'll also show you how to do numerical solutions for that type of problem. So we'll be able to approach it from two different directions. Here's a book on beams on elastic foundations. So this is written by the guy who basically came up with all these equations that we're going to be looking at. And, oh yeah, there's those hard to read ones. Oops, wrong file here. There we go. Wait. Hold on. All right. Oh, I was in the right file. I just forgot to clear the page for you guys so we can write notes together. All right, there we go. All right, so like I said, whole book. We're just going to spend a couple of lectures on this topic, but there's a lot more in this book that you can do with beams on elastic foundations. And what we're going to be really just kind of focusing on, picking out the simplest concepts and applications out of this book. So essentially, I think I mentioned this in the introduction to the class, beam on elastic foundation, one example would be a railroad track, right, where the soil represents an elastic foundation. But in reality, soils they don't have purely elastic behavior, right? There's definitely some elastic properties of soils, like, they can transmit sound waves and things like that, but it's viscoelastic technically, and so elastic models can at best be used as practical approximations. But that is what we're going to talk about in this class. I was reading through the introduction to this book, and the author was explaining that, in addition to soils, there are a lot of other applications, very practical applications to the beam on elastic foundation problem. And he mentioned networks of beams that would be, for example, a floor system in buildings, ships, etc., or very thin-walled circular elements like pressure vessels, tanks, things like that, corrugated metal tubes that are, have some function, maybe underground, maybe above ground. And with those thin-walled circular elements, the idea is that as they are, experiencing expansion or compression, if the radius is expanding or compressing, then it's changing, and that provides a kind of elastic foundation for the rest of the material. So it's interesting. I haven't personally applied it to those types of problems. In this class, we're just going to be thinking about, a little bit more abstractly, but thinking about infinite beams on elastic foundations. But there are some very practical applications to it. So with that, we'll get going. All right, so we have a beam on an elastic foundation, right? An applied force will generate a very localized disturbance. All right, so in other words, all of the deflections and internal forces will dissipate with distance from the applied load. All right, so you can sort of see a sketch here. Technically, the deflection, right, theoretically, the deflection would be symmetric about the applied load. I didn't draw it perfectly. And this lowercase k is the symbol we use to represent the foundation stiffness, all right, or the foundation modulus. And then the beam stiffness is represented by the product of Young's modulus and the moment of inertia for that cross-section. So EI represents the beam flexural rigidity. And so the solution to these problems has to somehow relate the stiffness of the foundation to the stiffness of the beam and how they would interact. So there are essentially two models that could be used for elastic foundations. On the left is what's called the Winkler model, and this is best described as thinking about independent columns that don't have any friction between them. So if you imagine underneath the foundation just a bunch of independent columns that can move independently from each other. So the theory then is that the deflection at any given point on the foundation, or the deflection at any given point on the beam, is proportional to the force, right, that's at that location as well. So we have something like this, which reminds me of some of those toys that you can get where you make impressions with nails or something. So if we consider this model, right, and here's a load, the stress distribution in response to that would be a normal uniform stress distribution, all right, something like that. On the other hand, with the elastic solid, you would have a non-uniform stress distribution. All right, so this is representing continuity within the foundation rather than these independent elastic columns. So your stress distribution would be high on the outer edges, something like that. Theoretically, right, it would go to infinity. And then it would do something like this. All right, so between those two models, since, as I mentioned before, soil is not a perfectly elastic material, it's viscoelastic in its behavior, both of these models would be imperfect. And so between those two imperfect models, it's ideal to choose the one that has an easier solution, right, which is the Winkler model. But in addition to that, as I was reading through this book, and this is, this was written a long time ago, but the author was saying that there have been a lot of studies that showed in some cases, a lot of soils will actually exhibit behavior that's more aligned with the Winkler model anyway. So it's not a perfect model, of course, but it might be even a better representation than some of the more advanced models that are out there. So it's nice when we can use this, when we can justify using the simplified model like that. All right, so now diving into this foundation modulus a little bit, if we consider a volume, a block like this, that has a cross-sectional area, call that A, we apply a force to it that would cause it to sink down into an elastic foundation. All right, so that the foundation deflects by delta. All right, if we measure it at the point below, the center point below there. We can write the normal stress, of course, as F over A. The normal stress is also going to be equal to the stiffness modulus of the foundation times delta. All right, and I'm going to call that, I'm going to add a subscript O to the lowercase k for now. So we can write K naught or K sub 0 is equal to sigma over delta. So this represents the force per unit area per unit deflection of the foundation. And so the units of this K naught value would be force per length cubed. In this class, we're going to be dealing with beams though, not areas. So if we consider a beam that has a width B, right? I'm going to write this down. K is equal to K naught times B. So that represents the force per unit length per unit deflection. So the application then would be for beams or any other line elements. You would want to use K. And then for plates or other area elements, you would want to use K naught. All right, so now that we've established that, we'll go into the beam equation for elastic foundation. So again, this was developed by Hetenyi. He's the guy who authored this book. And we're starting, as you notice, with the same sliver of a beam that we looked at last time in the regular beam analysis derivation, except now we have an extra term representing the stiffness of that elastic foundation, all right? So from equilibrium, when we sum forces in Y, we get the change in shear over dx is equal to kx minus q. And then from summing moments about the center of this segment, we get the change in moment over dx is equal to capital V. And down below, we have the sign convention for beam on elastic foundation. And as I warned you last week, it flips what we presented for the regular beam analysis, all right? So the difference is we take positive deflection as downward, all right? So that changes positive slope as well. And from these expressions, all right, applying our regular relationships from there, we can get moment deflection which would be m is equal to negative EI times the second derivative of deflection with respect to x. We can relate stress to moment. That's normal stress is equal to m times y over I. We can get shear force deflection. So that's capital V is equal to negative EI times the third derivative of lowercase v with respect to x. And from there, since we established that the change in shear with respect to x is equal to k times lowercase v minus q, we get EI times the fourth derivative of deflection with respect to x plus k times lowercase v is equal to q. So this is the beam on elastic foundation equation. Questions? It'll get more interesting. So we're not going to get through the example today, but we'll get through this next page. All right, so you may recognize that equation, right, as a fourth order ordinary differential equation. For convenience, all right, so that we can solve this without too much of a headache, we want to define a parameter so we're going to call this parameter beta to the fourth power. Equals k divided by 4ei, where beta represents the relationship between the foundation stiffness and the beam stiffness. All right, the units of beta are 1 over inches or 1 over millimeters. You'll understand the reason why later when we get on Wednesday when we get into applying this. And if there is no distributed load, which is the condition we'll consider first, and then later we'll look at cases with distributed loads. But if we have no distributed load, in other words, Q is equal to 0, then the solution to that differential equation is shown in the box below. So this first term, all right, and the second term are very similar to each other. They just have different constants of integration contained within them. And then the sign on the exponent is also different. So the first term essentially represents a solution that increases with x, or increases with beta times x, technically, right? That's not very realistic to our problem, right? Because if the beam is deflecting downward, the soil is deflecting downward, right? So the practical portion of our solution is actually this second term, where the function is decreasing with x. So that's the one that we're going to end up focusing on. And the rationalizing between that mathematically, all right, comes through boundary conditions. So it's explained down here in the first note. All right, solutions will die out with increasing x. So if we set those constants C1 and C2 equal to 0, all right, so we have 4 constants. We say those are going to essentially be 0 for practical purposes. Then we only need to evaluate C3 and C4. And we'll use boundary conditions to do that. All right, so that's where we'll pick up next time. Questions? No? All right. Yeah. Well, I'll see you all on Wednesday.